hope you remember what I showed before. So we will be studying anti-symmetric Lyapunov equations, or more in general, like zero-sum game in a replicator dynamics. So first of all, we said we have to look at S strategies, which could be any number of strategies. And in particular, we are, so we call each strategy EI, and we want to know how many players are playing strategy S, or strategy EI, and we call this number Ni at time t. Okay, so this in the end is the dynamics we want to look at, how many players are playing strategy EI. This, of course, has to be positive, because it's a number. And we want also the mass to be conserved. All right, so the sum of all n's stays always constant. Why? Because we only have, players can only change strategy, they cannot die. Okay. So what happens if we have one player that is changing strategy from EJ to EI? Well, it means that our vectors of n's is going from n to n plus EI minus EJ, where this is a base, right? So that's one from element I more, one from strategy J less. What is the transition probability of this to happen? So we call this G, I, so J going to I of Ni and J. Okay. Rij multiplying Ni plus Sij, everything multiplying Nj. So if you remember, we explicitly look at rock, paper, scissors, right? And we said we have this sort of reaction kinetics that is given by the replicator dynamics. So we say, well, when there is Ni, one individual from I and one from J that meet, they will transition with a certain probability Rij that depends on which of the two is the winning strategy. And they will move to either I or J, depending on which is the winning strategy. And so we just call this number Rij. So then now if we look at a population, it will be proportional to the number of individuals in each strategies, because the probability that they meet is exactly given by how many you have playing strategy I and how many you have playing strategy J. Okay, so if you only look at two individuals, the probability is only given by Rij. When you have many, it scales with the population size. Okay, the probability that they meet and therefore interact. And this inside is a sort of a mutation. So this is independent on actually J meeting I, is just how many of population J just decay, like they just have a decay to strategy I. So they just randomly mutate without the need to encounter an I. Okay? So we will set this as Ij for 0 now for simplicity. So this goes to 0. And then if we want to write the dynamics for Ni, we'll have something like Ni, time evolution of Ni, and we sum over all other strategy. So J different from I of R and I and J minus So you understand one is the gain, the other is the loss. So this is strategy J entering in I, summing over all possible strategies. The other is I moving, changing strategy to J. So over all possible strategies, you could change them.
I didn't get why we put the Sij 0.
Oh, this is just the choice for now.
Okay.
So we are really just looking at a game, pretty much.
Okay.
So the only way to change strategy is that you meet another strategy that is better than yours. This is what we're using. Okay, then if we introduce a matrix A, which has entries A, I, J, Rij minus Rji. This is an antisymmetric matrix, right? So we have that Aij is equal to minus Aji. And then we can write, we introduce now fractions of individuals playing strategies. So we introduce x of I as ni of t over the sum of all possible individuals. Because in the end we know that n is fixed, conserved, so it's enough to just look at the fractions. So the sum of the x sizes to be 1. Okay? And then what will the dynamics be like? It will be like this. And you see this directly from here, in which I'm just using the notation. Okay, so this now we will focus on systems that do something like that. Now we dive into the maths, we forget a bit about the background, but you should always keep it in mind. So now we want to study systems that have these properties. Okay, and interestingly, we will find that this dynamics is governed by a very special kind of function called the Lyapunov function. That really tells us a lot about the global dynamics. So we saw before a way to know about global dynamics, which was the Poincare-Bennigsen theorem. Now we'll see another way to know about global dynamics. Is any one of you familiar with what is the Lyapunov function? Yes? Oh, cool. Some of you. Nice. So first of all, we identify a simplex that so pretty much, this is our dynamics. We start from having that this is positive and the sum of all the fractions is 1. And we want to be sure that under the dynamics, this doesn't change, right? Because of the physics. So if the sum were to increase or decrease, we would have that the number of individuals is not conserved. So we don't want this to happen. Plus, if this were to get negative, this wouldn't have any meaning physically. So we want to be sure that those two conditions are in place also under the dynamics. So we define this simplex as those are just the conditions I wrote before, nothing more. And now we just look at what happens under time evolution. So now I'm just writing the multiplication explicitly. Okay, you agree? Matrix A acting on X, just Aij xj, sum over I and j. And now we do a very nice trick that sometimes helps, even if it looks trivial at first. So I just write this as 1/2 xi Aij xj plus the same thing again. And now what can we use to show that the time evolution is 0 and therefore the sum constant? Any ideas? Yeah?
That the Aij's are this much.
Exactly. So then you can just exchange, those are just dummy indices, we're just summing over them. So here you exchange I and j. Here you get the same for the x, just exchange them, and for a goes into Aji, which is minus Aij, so the sum is 0. Okay. So we are guaranteed that this time derivative is 0. So this stays 1. But we said we have two conditions to check. One was this, and the other is that we stay in this non-negative region, so that each component is non-negative. How do we see that? So we look more explicitly. We have that the time evolution of the logarithm of xi. Well, I'm just dividing this by xi. Right? Okay. Will be something like exactly, which is a xi. And this is true for all I with xi strictly greater than 0. But if this is not strictly greater than 0 but equal to 0, then you will just stay at 0, right? Because then you're just multiplying by 0. So nothing happens. So we can say, oh, let's restrict to the case where this is strictly greater than 0. Then we have this dynamics. And what is the solution of this? Well, it's something that looks like this. And this is positive. Okay, so we have the two conditions are satisfied, so we are guaranteed that our solution under time evolution will stay physical. So we will stay in the simplex, delta S minus 1. So now we want to study a bit more in detail what are the fixed points of this system. And then from what we kind of just discussed already, we have that a fixed point belonging to the simplex is stationary if and only if this is the definition of the stationary state. And this is true if and only if so either this part is 0 or this part is 0. Right? So either this is 0 and xi is strictly positive. We know it has to be non-negative. Okay? So either this or this. So we can rewrite the matrix A in a block form as such. And then we can rewrite these conditions. So, I mean, just get the star, that star. Right? I just really rewritten the conditions from before. I didn't do anything special. Well, now the question is, does a fix like that exist? A fixed point like that exist? And we cannot say, we would like to understand what happens, right, to the time evolution of our strategies. And the answer is that we cannot say exactly where those strategies or the vector of strategies will end up, but we know that some strategy will just be ruled out, so they will go to 0. And a smaller subset of strategies will be selected. And our dynamics will be really within this subset of strategies, which is why we call this a condensation, because only a few strategies are selected and we will stay within those strategies. And those are exactly the one picked by this I. So the ones that have positive entries for X. So the proof for what I said goes like this. Okay, I will not go into all the details, you can find it in the lecture notes, but it goes like this. So let's imagine we have a C such that those conditions are in place, so it is a fixed point for the dynamics. And the C has a certain support I, which is exactly what we did before. So it's the same as I find it above. Now we assume that this is a fixed point, so that A, C of I is 0 for I belonging to big I. But plus, we need something more. We want A, C of K for K into the complement of I. We want this to be strictly negative. Okay, then we have those conditions in place. And we want to know what can this tell us about the dynamics of a generic solution of our time evolution equation. And we introduce a Lyapunov function. That is the Kuhl-Blatt-Leiber divergence as such. D of C, okay, sum over indices in I, so in the support of C, in I, logarithm of C and over Xi. So this is a Lyapunov function. What does this mean? We know that under time evolution, this function can only decrease or stay still, depending if it's a strict Lyapunov function or not. This is not in general strict, but we know that this can only decrease. The proof, you can find it in the notes, but I just want to write explicitly what does the time evolution of this look like. So this is how it looks like, and well, we know that by this condition, this has to be smaller or equal than 0. Okay. Plus, we know that the xk are non-negative, each of them. Well, it can also be a strict Lyapunov function if the sum over the xk is strictly positive, but it's enough to have this now. So what does this tell us about the dynamics? Now, so we have this has to decrease, and this is how it looks like. So there are two main considerations we can do. The first one is, when will this be 0? This is strictly negative, this cannot be 0, so those have to be 0. Right? So for this to be 0, we need to make all the external components, external to I, to go to 0. So we know that our dynamics is condensating within I. So all the components of X that are external to I are dying out. This is the first thing we can say. This is quite powerful because this is again global dynamics, just because we know that this decreases. And the second thing is, this has a minimum. This one has a minimum, right? Because if xi is equal to ci, this is 0. And it's decreasing. It has a bound and it's decreasing. So we know it cannot explode. But what will happen if one of the xi's were to go to 0? Well, this would go to infinity, right? So we also know that this cannot happen. So we know two important things. We know each of the xi's will stay bound away from 0, will stay positive, plus the one external to the I set will go to 0. So we know that in the end, the only strategies that will survive will be the one within the set I. So we prove that we have condensation just looking at the dynamic of this function. Okay? Questions? Yeah?
Could you explain again, because I didn't get it, why can we express A matrix and fixed point X in this form on the upper board?
Here?
Yes.
So we want a stationary state, okay? So we want a vector X that each component doesn't evolve under time evolution, okay? So each component has to satisfy this equation. To satisfy this equation means that each component is either 0 or it makes this product 0, right? Because the product of these two has to be 0, okay? And this I'm just then splitting the components in a set where those are non-zero and a set where those are 0. And the set where the components are non-zero, I call it I. And this is what I'm writing here. And then I'm just reordering them if you like.
So I are just like indices of a basis that...
Of a subset, yes, of a subset of a basis, for which I have a stationary state that has positive entries. Okay, so this is what I'm doing. And then to prove what I said, the condensation, I'm using this Lyapunov function. Well, then one could ask, actually, so it's not the full story, because one could ask, well, but does the C like that always exist? Right? And the answer is yes, and this is not hard, and the interesting thing is you just have to satisfy algebraic equations. You don't have to solve the full dynamics, which is quite powerful. What I didn't prove, and it's the trickiest part, is that I is unique, right? Because you could say, well, but then if I find different C's that satisfy these conditions but have different I's, then you would have contradicting statements about the long-term dynamics. This I tell you, you can check it in the natural communication of Erwin. So the I is unique. So this is the underlying assumption that I didn't discuss. But otherwise, it all stays in the Lyapunov functions. Okay? So we can have a look at how this looks like in a numerical simulation, just to give you an intuition. Like the condensation, I mean. So those are all the possible strategies, and you see those arrows are just saying how you could transition from one strategy to the other. So you remember, like rock, paper, scissors, you have the rock, can go into paper, and so on. So this is just what this is representing. And then from all the discussion we have on the board, we know that a subset of those strategies will be selected, and the long-term dynamics will just stay in these strategies, within the set of the strategies. And indeed, if you look at simulation, we see that there is a subset of strategies, and in the long-term dynamics, we just stay within one of those strategies. So this is what's happening for S going to 50, for example, here. So we have the condensates and the depleted states. And this is just what we did on the board. We have a unique set for condensates. You have to believe me about this. We used a Lyapunov function to prove it, which is the Kullback-Leibler divergence. And one can show that the time evolution is negative. And this just identifies the condensate vector, where all the surviving states lie. Okay. So this was a bit of an example of how actually dynamical systems have a very broad application, and if you like these kind of things, it's something we could, for example, do in the seminar, for those of you who are following the seminar. And there, one can also study some topological phases and topological phase transitions by looking at eigenvectors for the stationary states of the dynamics. So there's a lot that one can do in this. But now we will have the last change of topic for the lecture of today, as I announced at the beginning, so we will talk about space, pretty much. And to do that, we have to go through a little bit of a detour, which is Brownian motion. So the diffusion equation is where we want to get to. So far, our time evolutions were always just about some density that doesn't have any space, right? It was just always the concentration as a function of time, no space. But of course, in physical systems, biophysical systems, also the coupling with space is very important. And how do we account for it? Well, in biophysical systems, there's one thing we cannot neglect, and this is noise, okay? And the space, so there is a noisy dynamics going on in space. And this is the Brownian motion. Let's look at a little video of, this is a nice historical, a little bit of a historical reference of how Brown told Darwin about his little secret, which is observing the Brownian motion. And this was known for very long, that if you look in a microscope, inanimate things like dust can actually move. And this was not really understood for a long time of like, well, why do they move if they are not, if they're inanimate? And there was a long, a long-standing hypothesis that this was some form of thermal fluctuation. And the person that actually proved this is Einstein in one of his 3 papers from 1905, the miracle year. And then actually Perrin got the Nobel Prize for this because this was a way to prove the atomic hypothesis. So it is actually very important, and it's really the basics of every kind of theory that has noise in it. You need Brownian motion, and you need to connect Brownian motion to the diffusion equation. Okay, so let's go on the board and go in a little bit more detail on this. So the topic is the diffusion equation. So this is really like our harmonic oscillator for people in biophysics. It's really, really important. And what did we see in the video? We saw particles that are undergoing Brownian motion. What does this mean in a bit more of a detailed way? Well, it's kind of trajectories for single particles are made of independent random jumps. Okay, so this is what Brownian motion means. And what Einstein showed, and if you want to go into the details of this derivation, you can also have a look at lecture, I think, 3 or 4 from the course that Erwin gave last semester. So it's stochastic dynamics of particles and fields. This means that the density of these particles undergoes diffusion. Okay. What is conceptually crucial for this to happen is the central limit theorem. So meaning that whenever you have, so here we said we have these independent random jumps. If those independent random jumps have like a zero mean, which you can imagine because you have a particle and it's moving right and left and back and forth, so the mean will be 0, and the variance is finite. So this is all you need. Then you get the diffusion equation for the density. So this is the central limit theorem that is in the background. So this, I said it's shown by Einstein, but another important thing that Einstein showed is what does so the diffusion look like. So diffusion is of the order of kBt, so that's what I said at first, thermal fluctuation, and it scales also with the friction coefficient. Dissipation. And, well, what is the typical kBt at room temperature? It's around 4 picomutons per nanometer. And this is a very typical energy scale that you would find in a cell. So this is why we care in the end. This is why we use diffusion equations, because at the energy scales we look at in biophysics, random fluctuations given by thermal fluctuations matter. Right? So you could say, well, condensed matter would be something like kBt going to 0, biophysics is kBt around 1, or kBt matters. It's the energy scale we look at. All right, so this was a bit of an introduction. And then maybe in the last 10 minutes, I want to show you how you can solve the diffusion equation using Fourier transform. I don't know how many of you are familiar with Fourier transform. Are you guys? Then I think I'll go through it kind of quickly, just so we're sure we're all on the same page. So first, we can go through like a sort of a heuristic definition, a heuristic derivation of the diffusion equation, just given by continuity. I'm not sure how many of you are familiar with the continuity equation. But it's just that mass cannot disappear. So that if mass is changing over time, there is some flux of mass moving. So this is what this says. And then a typical way to get to the diffusion equation is just to say, well, but what is the current like? Well, the current just does something like that. This is my concentration. So I'm just saying it goes from high density to lower densities. That's how our mass moves. This is called Fick's law. This is a heuristic kind of reasoning. And then you get what we want. Okay, so this is our diffusion equation. So let's Fourier transform this. I will use the convention that my Fourier transform C of k t. So we'll use the one with the plus here. I take x, c, x and t. For the anti-Fourier transform, you have to divide by 2 pi and put a minus here. Right, so how does this read in Fourier transform? How do we solve this? Sorry, this got really too funny. But we want to know how does the concentration in real space evolve, right? So what do we do? Yeah?
The inverse Fourier transform.
Exactly. Well, now we reuse the definition of the Fourier transform for the initial condition. And now we want to perform the interval in K, such that we end up with like only an interval in space. What can we do for the integral in K? Any ideas? Exactly, this is a Gaussian integral, so we need to complete the square. Have you seen this before? Yes? So you have to rewrite this as some k squared with some prefactor. Okay? I will just give you the result, but if you don't know how to do this, you should. So just look at it. Yeah?
Oh, it's written in sheet 0.
Oh, great. Right. So you should all know how you do it. Great. So I can just write the result. Okay. So we get integral instability is fine. So this is what we get from the Gaussian integral in K space, and this is what we get from the remaining term from completing the square. So what we get is that at time t, our solution is a convolution of the initial condition with like a Gaussian Green's function. Okay? And we see that it's decaying over time. Right, so this is the kind of solution that you get in general when we are just looking at the infinite line. So here we're just looking at the infinite line in one dimension. Now I just want to write down how much boundary conditions can change the solution of the diffusion equation. So we will look at no flux boundary condition and Dirichlet boundary conditions. This will be quite quick, but I think it's important that you keep in mind that whenever you're solving a differential equation, you need to know what are the boundary conditions because it can really change a lot. Okay, so we can see how this changes the solution to the diffusion equation. So we have a segment on the infinite line between 0 and L, and we want there to be no flux at the boundary. So the derivative in x has to be 0 at 0 and at L. But at stationary state, we have that diffusion equation just reads something like right? But then what does this imply? Right? So we just integrate once, and we get that the derivative in space has to be a constant, but then this constant has to be 0. If the derivative is 0, C is a constant. So the steady state of a no-flux, one-dimensional system is a constant. If instead we have Dirichlet boundary condition, so this means we want to fix the density values at 0 and at L. Again, by the same reasoning as before, we have that x of c is some constant a, but then we can integrate c of x, and it becomes a of x plus b. And then we can just use the Dirichlet boundary to get that a. Okay, so you have seen what is the general solution of the diffusion equation, how it evolves over time, and then if you look at the steady state, you need to take care of the boundaries. Any questions on this part? Okay, otherwise, next lecture, so on Friday, you will see with Erwin how coupling now reactions, which is what we did before, with diffusion can give rise to very interesting patterns in a more realistic setting than what you've seen before, because before, if you remember, we had no space, and now we actually are looking also at spatial coupling. So thank you very much, and see you on Friday.